check, you can hear 100% infill. Huge thing here. This is also on island. I mean, can you even see it 3D printed? Oh no, even play around. It's very nice. So we are in the lab. 40mm cube. Whoa. Be mine. All our different materials. How do you guys like this? I think we are live. Hi everyone. How's everyone doing? How is Wanraz doing? How is Steven doing? How is Michael doing? How is Trophiolite doing? Slim Pickings. Quick, everyone change your name to Mark. Let's go. I'm ready for my free roll of filaments. Great, Michael. And that reminds me, let's get some awesomeness here. Let me start that giveaway. There you go. Okay. Where's my banner? Where's my special banner? There you go. Who else do we have? Gianna, Situ, thank you for joining. Non-fam. Kiwi Dang. You're doing great, Steven. Awesome. Great. And then we have some awesomeness in the chat. Perfect. Hi, Zalan. Thank you for joining the stream. So today, Sophia, thank you for joining. So today we're gonna have a special PRINTBUSTER stream. So do you remember we had for those that are following the Polymaker Hangout every Saturday, we are basically every Saturday we are discovering a little bit some new technology, talking a little bit about stuff on the market, and then trying to understand a little bit more some topics. But recently I've noticed two main topics that I think can have an episode on itself. The first one at hotends. I think there's so many different hotends at the moment, and then many different names and stuff. So I was thinking, maybe PRINTBUSTER would be a better stream to really dive into, what is a hotend, and then what's the difference between different hotend and stuff. So the second are Clipper. So I think Clipper is doing a lot of different stuff, which I still don't know exactly how it works. But I think a full episode on PRINTBUSTER would be better for that. So this week we are going to spend time on hotends. We are going to learn, what is a hotend, going a little bit back to the basis, even though it might look like basic knowledge. But to be honest, when we really dive into that, then there is some stuff that I didn't even know about hotends. But anyway, that would be for today. And then for next week, it will also be a special episode, and that would be more on the firmware and more focused on Clipper, like what is Clipper, what it can do, how it does that, etc., etc. So that would be the deep dive that we're going to do this week and next week. And then after the week after, then we can go back to our regular PRINTBUSTERS topics, which is warping, the benchy hull line, wet filaments. What else do we have? Food safety. And one more, which was what? Let me check again. Flow calibration. Yeah. So these regular topic, because I almost finished the to summarize everything. So it's going to be online by the time we will go back to this topic. So I hope you guys are excited to learn about hotends. I am personally. Hotends is one of the most important part of the 3D printer, and it defines a lot of limitation of the printers. So I think we are not going to dive into the cooling part, like fan deck design, and then different kind of cooling fan, and then how to handle the airflow, etc. We are only going to focus on the hot end itself, like nozzle, heat break, heat sink, the heat block, etc., etc. So that's what we are going to focus on. Okay, we have more and more people joining. That's great. And obviously we have more awesomeness with more people coming. Jan Drygi, how is it going? Very well. How are you? Just me. I'm awesome. A lot of awesome people joining. That's so cool. Twilight PA Pro is my favorite. Nice. We did spend a lot of time designing that one. The great balance between the rigidity and the toughness. Glad you like it. Today I found my old stock hot end on my desk. I should make some order on my desk. Yeah, keep the old hot end. You can dissect the hot end to learn a little bit more about it. It's always good to keep spare parts to diagnose the part. You talk, I listen. E3D Hemera for the win. Yeah, there's a lot of names. So let me show you what company I selected, and then you can let me know in the chat if you know some other companies. So the one I selected, the first one is E3D. So I put them by rank of popularity. I rank them by popularity, in my opinion. But I'm not a big expert in hot ends, so let me know if you agree with that ranking, and if not, what would be your ranking? And if someone is missing, let me know. So today we are going to talk about E3D nozzle, which seems to be the most popular hot end design manufacturer, hot end designer and manufacturer. So that would be the first one, E3D. The second one would be Slice Engineering, also hot end designer and manufacturer. The third one would be Dice Design, and then would be ProtoPrint. So ProtoPrint, I think there's a lot more, but I chose this one because I basically googled hot end 3D printing, and then I took them by order of appearance on I think it was page 1 and page 2. And I think page 1 you had E3D, and then I think you have E3D, Slice Engineering, and Dice Design. And then on page 2, the first one was this one, ProtoPrint. To be honest, I have never heard about ProtoPrint before, but let me know if there is. Then there is BombTech, but BombTech is actually using Slice Engineering hot end, and I guess they're really focused on their extruder more than the hot end. I think the hot ends are more from Slice Engineering, and it seems like 3D Solex is another one. Let me check. 3D Solex AA PB. Okay, so you also have that one, but I haven't found it on. So BombTech is not. So we have 4 companies: E3D, Slice Engineering, Dice Design, and ProtoPrint. So is there any that you think would is there any hot end manufacturers that I missed, like popular, like more within the popularity of this one, or at least the top 3, Dice Design, E3D, and Slice Engineering, to make sure that I have all of them. Now we can study all of them. Oh, MicroSwiss. Okay, just received my first roll of Polymaker PLA filament. Can't wait to print this weekend. Yeah, looking forward to your feedback. Jitmon on our filament. I want to talk about this hot end. Great hot end, just pricey. Wait, what's the heck? Where is MicroSwiss? Okay, MicroSwiss. Let's. I just added MicroSwiss. NG on my ender runs great. MicroSwiss. Okay, so let's go to MicroSwiss. hot end. Okay, so let's add this. And what do you think? Shall we keep that one? I mean, protoprint. I mean, I've never heard about them before, but they explain things pretty well. So maybe we should keep it. Micro Swiss, and then let's go to their main website. Extruder kit, all metal hot end, nozzle, and stuff. And then what do we have? We have hot end. Yeah, hot ends. Okay, and then we have Micro Swiss. Okay, any other that I forgot? Will you be diving into the slice drama with the maker Voron Fidges community? No, not today. Not today, quick. Today would be really about understanding hot ends and what are the differences between the different hot ends. Especially going through the marketing war of the different company, and really, getting data and looking at their different technologies and design. I really want them to finally release the Obsidian Revo nozzles. Would instantly use up the rest of my stone field filament. I might get some carbon field from Polymaker. Okay, so the first thing I want to do is I found this article from Filament to Print, and it's pretty good on going back to the basis on what is a hot end. So I want to spend 10-15 minutes first defining the different part of a hot end, and then for each part what makes it good and what makes it not good, for example. So let me give you an example. So you have the hot end here. So first I'm going to do it live so that we can check together, right? So first you have, if we go from bottom to top, and we have to do this together, right? Because there is some stuff that I'm not familiar with. I mean, I'm in the material industry, not the hardware industry. So obviously you have a whole bunch of different way of designing your nozzle. So the nozzle is a big part of the hot end, how you make your nozzle. The other one is so for nozzle, let me just talk a little bit more about nozzle. Nozzle is you have the material that is used to make the nozzle, and you have the geometry. Okay, I think you only have two things that define the nozzle: the material, like is it a hardened nozzle? Is it a brass nozzle that is coated with something? Is it metal that has been heat treated in a particular way? Blah 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 blah. So you have the material part, like how it has been, like what was the material used for the nozzle. And the second one is the geometry, like how is it designed inside for the flow of the filament. Is it a steep angle? Is it a steep funnel, or is it a wide funnel inside, or the size of the nozzle? Is it a 0.4? Is it a 0.6, a 0.8, a point whatever? And then how is it threaded? Or is it a long nozzle? Is it a short nozzle? Or what's the relationship between the dial length and the nozzle size? That would be important for stringing, for example. So you have the geometry. So for me, nozzle is only defined by two things: material and geometry. What else? CHT nozzle. Yeah, CHT nozzle for me is geometry. It's a different geometry. My go-to far hot end are the 999 creative style. I like cheap, and that worked just as well. They all just push plastic through a 0.4 hole. Yeah, I mean, the goal of today is to understand that, right? Are all the hot end pretty much the same? And then it's all marketing behind, selling that hot end better than another one. The goal of today is to understand a little bit more about it. Maybe coating is its own category. Yeah, it could be. Okay, so I was including that in material, but we could have it separate. So you have the main material and maybe coating or maybe should I say treatment, maybe some treatment like different nozzle are treated differently, whether they're coated with something, they are heat treated, they are, I don't know, some kind of treatment that are given to the nozzle. But let's say these three, as far as I know, define more or less the differences between nozzle. So what are the difference between this nozzle or this nozzle? It would be either the material, either treatment, either geometry. There cannot be any other different other differences. I mean, maybe compatibility. This nozzle is compatible with this heater block, and then this nozzle is compatible with this heater block. But let's put compatibility aside for the moment. Bimetal heat break is the only major game changer. Well, we're gonna look at this. What are the differences between the different hot end, and is there any breakthrough technology that one of the companies is using or not? Blah blah blah. Anyway, so the second one, going from bottom to top. The second one is I guess it's called the heat block, right? So heat block is the same. I guess you have material, maybe treatment if there is any for the heat block, and the geometry. I don't think there's anything else that differentiate one heat block to another heat block. Yeah, let me know if you see anything else. But even treatment, I wouldn't put it inside. I don't think. I mean, it is possible to treat the heat block in a certain way, but I would say maybe it's less important than the nozzle. So one manufacturer to the other manufacturer, I guess the main difference would be on what material they use. Even though I believe they all use brass, right? You know what? Maybe I will remove material. Is there what I want to highlight is factors that we are going to see differences between different manufacturers. So, but I think, and let me know if I'm wrong, but I think they're pretty much all brass, or they all use the same material. So maybe I will remove material. There might be some with a different material, but I don't think that's yeah, I don't know. Somehow I have the feeling that material is not very important from one manufacturer to the other. Hi, Robert. Hello, Han05. Thank you both for joining. Don't forget to be awesome. So the next one, again, let me know if I'm forgetting anything. But the next one is what's going to be in the hole here. So you will have the and that's where I need to get the good vocabulary. But there is something that is called the thermocouple. So the thermocouple is what's going to heat up the let me check. It's going to heat up. It's like a resistor, right? Let me check. A thermocouple is an electrical device consisting of two dissimilar electrical conductor forming an electrical junction. A thermocouple produces a temperature-dependent voltage as a result of Seebeck effect. And this voltage can be interpreted to measure temperature. Thermocouple are widely used as a temperature sensor. Oh, okay. No. Sorry. The thermocouple is not the thing that the resistor is the thing that's gonna heat up, and the thermocouple is the thing that's gonna, depending on the temperature of that thingy, like the thermocouple, and then it will generate a different voltage, and that's how you measure the temperature. Okay, my bad. So, and how do you call the other one then? Just a resistor. Let me check if they have that vocabulary here. So the thermocouple, okay, here. The thermistor is the most common. It has a high. No, but that's the temperature probe. Probe means just to check the temperature, right? It is the element responsible for measuring the temperature of the heater block. They are okay. But what I'm interested in is what is heating up that heat block. How do you call that? Just the resistor? Is it? It is the element responsible for transmitting heat to the nozzle and the hot zone of the heat break. There are mainly two types: normal and high temperature. Standard heating block are generally made of aluminum. Oh, sorry. So they are generally made of aluminum, not brass. Really? I thought it was brass. The heat block, I thought it was brass, not aluminum. They are the most economical, but only withstand temperature up to 300 degree. High temperature ones are made of nickel plated copper and can withstand temperature up to 500 degree. Okay. Some, such as those in the V6 system, have as option a silicon case or sock that help protect the piece from irradiated heat, something of particular importance with materials such as PLA. Okay, yeah, I understand. So there's no particular name. But you know, when you buy a nozzle, you have, or is that the same? Yeah, you always have two things, right? You have that one, the big one. How do you call the big one? Just the resistor? Oh, heater cartridge? Is that how you call it? Let me check the chat. I'm pretty sure you have the name already. Do you have mounting option? We are not, Zombie. I'm not too sure what you mean by the mounting option. But if you are referring to the different brackets that join, you know, the hot end to the printer, we're not going to talk about compatibility today. Yes, I got your email, Rover. As far as I know, only high temp heater block use maybe plated copper. Yes, yeah, I just saw that on the article. Thermocouple measure temperature, not the heater. Yes, thermocouple measure the temperature. I think you wanted heater cartridge. Okay, so it's called heater cartridge. Some heat block are aluminum, other are copper with plating. The heater cartridge is heating the block. Okay, thank you guys. So you have the thermocouple. So the big hole, I guess, is for the heat. So you call that heat cartridge, right? And then the small hole, which is not there. But I think it's a different hole. Let me check. I'm pretty sure it should be a different hole. Yeah. You see, the big hole, I think, is for the cartridge. The small hole, I think, is for the thermocouple. I don't think they are in the same hole. I don't think they are mixed together. I think there is always two holes. But let me know if I'm wrong. But somehow this schematic doesn't have the other hole. But you have the heat cartridge, and then here you have the thermocouple. So the heat block, what we just learned is either aluminum, so that would be up to 300 degree, or copper, nickel. So it's nickel, and it's plated in copper, right? That's what they were saying, for 500 degree. So let's check. Nickel plated copper. Oh no, sorry, nickel plated copper, and that's go up to 500 degree. So you basically only have two type, more or less, and that goes up to 500 degrees C. So yeah, there you go. And then the thermocouple, okay. Heat cartridge. So for the heat cartridge, what are the different? Can you have a heat cartridge? Can you have a heat cartridge better than another one? Maybe not. No. Heat cartridge are always the same. Heat cartridge comes in different wattage. Oh yeah. Good point. So I guess the power of your heat cartridge. So I will just put so maybe just power. So maybe some heat cartridge can heat up faster than other. Is that the power? Is that the power is about the speed, or is the power about how hot you can get? You get what I mean? Like yeah. Is it how hot you can get, or how fast you can reach a certain temperature? Like pretty much all the heat cartridge go to the same temperature if you leave enough time. But if you have more power, then you will reach that temperature faster. or you can maintain the temperature. Yeah, I guess. Let me think. Or both. How well a hot end is mounted makes it more stiff and prints better. Yeah, like I say, Zombie, we won't talk too much about this. We will talk really just about the hot end itself. Yes, small is the sensor, big is the heater. Okay, got it. Just catching from minutes ago, heat blocks are usually brass, but some cheap one are aluminum, and some expensive one are copper zinc coated. Okay, I thought it was brass, but this article says standard heating block are generally made of aluminum. So either the article is July 6, 2020. Huh, okay, FDAF patch. So you are challenging that saying. So maybe let's do a little bit more research. So heat block, hot end, brass. Let's just force him to find some brass stuff. Triangle Lab V6 brass heat block for hot end, blah, blah, blah. This brass heat block is suitable for various equipment. You know what? Let's just check the V6. I guess the V6 is one of the most popular, so let's just check the heat block of the V6 is made of what? E3D V6 heater block for sensor cartridge, V6 block cartridge alu. So I guess the ALU means aluminum. So I guess actually it's easy to see because I think the brass would be yellow. I mean, kind of orange yellow. Oh, actually, you know what? Here. Okay, so you have aluminum plated copper look like this and brass look like this. And to be honest, I have seen much more gray one than the other two. I mean, I did see plated copper, but I don't think I have memories of seeing this brass one. Maybe. But okay. So what would be the temperature for brass then? So you have some other that are brass, but I don't know what could be the temperature. For example, a Creality heater screws right through the heat sinks, but a V6 uses a collar mount, which might have more play. I have a copper V6 block. Okay. How long will the live stream be? I have no idea, 105. I never know how long my live stream is going to be. Zombie, yes, you can. Some of them are resistive tubes, other are ceramic and surround the whole nozzle. Yeah, I don't remember what question you're answering. E3D would say heat cartridges can vary greatly in quality. Okay. Oh, so it was about the heat cartridge. So yes, you can. Some of them are resistive tubes, other are ceramic and surround the whole nozzle. Oh, okay. So you also have a question of material, right? Inside the heat cartridge, the power of the material. More power is needed for higher flow hot ends to maintain temperature. Most heat cartridges are basically the same. Revo is a bit different in that it has positive thermal coefficient. Basically, can't overheat. Revo is a bit different in that it has positive thermal coefficient. What's thermal coefficient? Different rated cartridges affect speed to achieve temperature. Okay, that's what I was thinking. Aluminum is standard for Creality and stuff. Higher power is both faster and can go hotter. Okay, got it. Most I know are aluminum. Actually, what is the real V6 block made of? Well, I don't know because there's so much. I don't know what's the real V6. I mean, maybe you know what? Maybe if we go to extruder and hot end, V6. We can just check the color. Oh yeah, we cannot check the color. Yeah, it's aluminum. So that's the V6. That's the standard V6 on their website, and it's aluminum. And it doesn't seem to have an option for to change that. Volcano, blah blah blah. Bowden pre-assemble, nozzle fan pad pre-assemble, blah blah. Yeah. So looks like aluminum is more or less the the V6 is the flagship hot end featuring all metal design, high temperature performance. That's also interesting. Like they say high temperature performance, but this article just said that that's why it depends. Each of the company has their definition of high temperature, right? Because for them, they say that you know the general economical way is we stand temperature up to 300, and then high temperature would be up to 500. But when you look at or is that nickel plated copper? No, it doesn't seems like so. It seems like just aluminum. Let's download the data sheet. Maybe there is more information. Or do they give high temperature performance? The benefit of all metal design can comfortably reach 300 with the supply thermistor. If you'd like to print at higher temperature up to 500, you will need to use a plated copper heater block. Yeah, so there you go. It is a high temperature, uh, but you will have to upgrade. But wait, but how do you upgrade? They don't. Um, 24 volt, 12 volts, pre-assemble, full range brass nozzle. Yeah, anyway, so I'm pretty sure it's aluminum, and then they say if you want to print to 500, then you will have to upgrade your heat block. Blah 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 blah. Okay. I think brass is just around 300 as well. Okay, I will just believe what you're saying without checking. Let's just put 300. Aluminum is standard. Copper is higher end due to better performance, but needs nickel plating to prevent corrosion. Yeah. Oh, okay, that's good to know. So I was thinking, why do they need nickel plating? So it's to prevent the corrosion. You can tell if it's a copper block because it's heavy. It's heavy. Okay. Power, it's for all. Higher power cartridges reaches the temperature faster, have a higher thermal capacity to keep melting higher flow. Maximum temperature are not that different in the typical news. But I thought the thermal capacity would be more important for the heat block, not the cartridge. The hotter the Revo gets, the more power it needs to get more hotter. Yeah, understandable. It is very old design, so that makes sense. The E3D V6 Anniversary Edition had the copper block. Okay. How old is the V6 now? I have no idea. V6 is aluminum. V6 Gold is plated copper. Okay, got it. Okay, so next, we have this piece inside. So this piece inside, I think, is called the heat break. So this piece is meant to break the temperature. Do you say break the temperature, or it's meant to insulate the cold end from the hot end? So maybe we should define these words as well. So in my understanding, this and these are different. So in my understanding, this is called the hot end, the actual hot end. Okay, let me move my let me move my stuff a little bit. Okay, so this is called the actual hot end, right? And this is called, I think, the cold end, the cold end. Okay, so to go from hot to cold, then you need some kind of insulation in between, and I think that's what this piece is responsible of. So I guess it's called the heat break. Okay, and heat break, there's a lot. I think there's material, there's geometry as well, design. I mean, I guess the heat break. I will just put design because I think that's one. I think this piece is one of the pieces that can make a nozzle better than another one. I think. I think the way they designed that piece is very important. The way the technology the technology or the design they find in order to insulate the hot end to the cold end from the hot end is I think makes a hot end better than another one. Much more important is the heat break. A bimetallic like slice actually extend the melt zone, where a standard V6 design actually prevent half the heat lock from efficiently transferring heat. Yeah, so we're gonna look at the different heat break design. Mark Kondraka, don't worry, you're never late. Don't forget to be awesome. It allows a limited amount of heat through in order to allow regulation in the block, aka a controlled leak of heat. Yes, the bigger the cartridge, higher the thermal capacity. The bigger heat block, higher the thermal mass. Okay, so maybe let me check. What is the difference between thermal capacity and thermal mass? Thermal capacity. Heat capacity, thermal capacity, is that the same? Yeah, it's the same. Heat capacity or thermal capacity is the physical property of matter defined as the amount of heat to be supplied to an object to produce a unit change in its temperature. Oh, the SI unit of heat capacity is joule per Kelvin. So it's the amount of energy you need to give to a material in order to raise its temperature. Defined as the amount of heat to be supplied to an object to produce a unit change. But does that mean the lower the heat capacity, the better? Because then you don't need a lot of energy to raise the temperature of your yeah. Is that if I understand it properly? Well, let me check. Is defined as the amount of heat to be supplied to an object to produce a unit change in its temperature. Yeah, so that means if you have a low heat capacity, it means you don't need a lot of energy, which means electricity. So which means a low heat capacity cartridge will heat up to a higher temperature without as much energy. So that's on one side. But I guess the issue is on the other side. Maybe the lower the heat capacity, the less energy you can transfer to another matter, to another material. Because, yeah, but that's the same. If the heat block has a low heat capacity, then it means the heat block doesn't need as much energy to increase its temperature. Sanjay once told me in chat that a larger than 40-watt cartridge in a VC blocks is just a waste. A larger cartridge doesn't help unless you have a sufficient block melt zone to use the heat. Okay. This is why the volcano is so long. Okay. Higher heat capacity will have a more stable temperature. Non-fab, no, that part is the conductivity. But it doesn't matter, right? Whether it's high conductivity or low conductivity, you still have, if you have the heat cartridge with a low heat capacity and the heat block with a low heat capacity, then it means both will need less energy to heat up to higher temperature. It depends. If you want a low power and low energy, you have a low filament flow. If you want a bigger flow, you need a bigger thermal mass, so you need a bigger cartridge and bigger path. Yeah, but let's put flow aside, because it for me, flow, flow is not important. What is important for me is the temperature of the nozzle. The higher the temperature of the nozzle, I mean, in any case, the most important is the temperature of the nozzle, right? I don't think we should involve flow inside the discussion, because flow has so much more into that. There's flow is pressure dependent. It's not only temperature dependent. It's as pressure dependent than it is as temperature dependent. So I think we should leave the flow aside. But the temperature of the nozzle, what I understand now is that the heat is doing like this. It's going from the PCB as electricity, and then it's heating up this cartridge, right? And then this cartridge is heating up the heat block, and then the heat block is heating up the nozzle, and then the nozzle is gonna heat up the filament, right? So what I want to understand is why. What it appears that you are saying that the higher the heat capacity, the better. But maybe that's not what you meant. But when I read this, is defined as the amount of heat to be supplied to an object to produce a unit change in temperature. When I read this, in my mind is like, okay, so I should choose materials that has a low heat capacity so that I don't need that much energy to heat them up. But at the end of the day, maybe we should make a difference between temperature and energy. Because maybe low heat capacity, you have a high temperature, but low energy. And the high heat capacity, you have low temperature, but high energy. So now what's important, the energy or the temperature? Because at the end of the day, we talked about energy transfer, not really temperature transfer, right? And at the end of the day, we need a lot of energy to arrive to the filament so that the filament raise temperature. So maybe that's what's wrong with my explanation, is that I'm thinking about the temperature being important, but maybe we don't care about what's the heat block temperature. We care about the filament temperature. So that means we care more about the amount of energy that is transferred through all of that path, from the PCB to the heat block, to the heat block, to the heat cartridge, to the heat block, to the heat nozzle, to the nozzle. Conductivity will affect the block heat transfer to the filament. Yeah. And then, so you first have all of that energy. So you start with a certain amount of energy, and I guess as you transfer from all of these steps, then you arrive with a lower energy. And conductivity is going to define the efficiency, is going to define the percentage of energy you have at the end compared to what you had at the beginning. So I guess that's that's where the conductivity comes in. Where the heat capacity comes in is maybe you can take more energy. Maybe the cartridge, you can give it more energy to raise the temperature. Well, there is still some issue with my explanation, which I don't understand. But heat capacity in the heat break. The more capacity, the more heat it can pass through. You want a limited amount of heat leaking, enough that the cartridge can keep up reheating. But it doesn't seem that the heat capacity has something to do with conductivity or pass through. I mean, from what I understand, they just say the heat capacity is defined by the amount of heat to be supplied to an object to produce a unit change in temperature. Joule per Kelvin. Yeah, so it's basically, how much energy you need to give. Like, for example, for my pen, so let's say it has to be a uni material, right? But let's say I only take the tip of my pen, okay, which is most likely ABS. And then how much energy do I need to give to this small piece in order to go from 25 degree to 30 degree? And that energy, if I want to calculate, then I will have to use the heat capacity of ABS. best way to explain is there is three ways for heat to escape a block, through the nozzle side, through the heat break, and through the block itself. Blocks have a sock to contain heat. Yeah, so Zombie, the question we are trying to answer here is it better for the heat cartridge or the nozzle or the heat block? Is it better that they have a high heat capacity or a low heat capacity? For example, the heat block, the heat cartridge or the heat block, yeah, whatever. Is it better to have a high heat capacity or a low heat capacity? And why? Heat break needs the lower thermal conductivity. Yeah, but that's conductivity. That's different. Maybe we can talk about conductivity after. Or are you saying that they're related? They're kind of the same? The total amount of heat leaking has to be... But why are we talking about a leak and the heat break or this kind of thing? The more stable temperature the heater block can be, the more consistent distribution can get in the filament. Yeah, okay. Heat breaks needs to be transmit. Heat breaks need to transmit the least amount of heat possible from heat lock to heat sink, the heat block to the heat sink, both end. Yeah, again, that's conductivity. That's the heat break, blah, blah, blah. Right, that would be equal amount energy coming from the heater and leaving the nozzle. From what I remember, the energy transmitted to another body by contact is conductivity, and capacity is the energy to raise by 1 degree. Yes, Nanfa. So conductivity is different from capacity, as far as I understand. So now the question is it better to have high heat capacity material or low heat capacity material, and why? Sosh Sekol, that's why Revo has super thin stainless leg between brass and earth, some slice. Yeah, again, I think that's answer a different question. Excess heat has to be dumped in a controlled manner. Yeah, I'm not sure. Maybe I'm late with the chat, but that what I'm trying to understand is really. Let me put my Discord away from. Yeah, what I'm trying to understand is really why this heat block. Or did I say heat break? No. So I'm not talking about the heat break, right? I'm talking about the heat cartridge, the heat block, and the nozzle. These that are responsible of bringing energy from the electricity to the filament. These guys are on the path, right? Of course, there is some conductivity thing involved. What I'm interested in is these material. Is that better that they have a high heat capacity or low heat capacity? Is that better that you need a lot of energy to raise their temperature, or is that better that they don't need a lot of energy to raise their temperature? Yeah, Zombie. I think I was late with the chat. So you guys were talking about something, but I was talking about something else. So the question is this. The question is that better than my heat block, my heat cartridge, and my nozzle has a high heat capacity, or is that better that it has a low heat capacity? Because from the explanation, a low heat capacity seems to be better in a way that you need less energy in order to bring them to a higher temperature. So let's say you want to print at 200 degrees, then maybe you only need 3 watts. Or I don't know how to, you need a less amount of energy because they have, all your materials are very low heat capacity, which means they don't need a lot of energy to raise their temperature. So your nozzle temperature can reach 200 degrees much more energy efficiently than high heat capacity. So with that logic, it seems that it's better to choose material that has a low heat capacity. So do you guys agree or not? Because it seems that it's counterintuitive, because if someone would have asked me without thinking, I would say high heat capacity, then they can have a lot of energy. And then, I don't know, the more energy, the better somehow. But it's not logical. So either my logic is correct, so you need low heat capacity material, or my logic is wrong. You need energy somehow. The difference will depend on how much heat leak from the block. Okay, the heater block needs a high heat capacity for more stable temperature. Okay, so what you're saying is it's about temperature stability, like someone else said above. And okay, so what you're saying is low heat capacity means, okay, because if you give a little bit of energy, then it's going to change the temperature. A little bit loss of energy, then it's going to change the temperature. But what you're saying is if there is a large heat capacity, then you need a lot of energy to change the temperature. You need a big energy change in order to change the temperature. So that's why it's more stable. Okay, understand? Makes sense? I would say high heat capacity to maintain good temperature when there's a difference of flow, but a high conductivity to spread the heat evenly. Okay, so temperature stability, like Zombie said, okay. It's a balance between all the things. Yeah, as always. You need a filament with low capacity, so it's easier to melt, okay, yeah. A block with high capacity, so it loses energy slower, and adjust the cartridge to be enough to keep the block at good temperature. Yeah, okay, yeah, makes sense. Start to make sense. Wooden low heat capacity parts wear out faster. I have no ideas on that part of timbers. I don't know. A higher heat capacity and overall higher thermal mass. Okay, so I still haven't learned what is thermal mass, so I will have to check. But a higher heat capacity and overall higher thermal mass heat block will take longer to heat up, but will have more stable temperature while extruding. Yeah, okay. So now we get there. So it's all about temperature stability. Only the area directly around the nozzle needs to be the correct temperature. If there is a low capacity, it will drop very quick and will take longer for the heater to recover. But the higher capacity will change temperature slower, allowing the heater to recover a consistent rate. Yes, okay. I understand 100% now. You guys are awesome. You guys are really awesome. Okay, so I will summarize to make sure I understand properly. So you need a high heat capacity. The main reason is it's like a big ball that you leave outside. If let's say outside you have some wind, then if the ball is very light, low heat capacity, very light, then the wind can blow that ball everywhere, right? The ball will not be very stable. But if that ball is very, very heavy, then it would be very, very stable, right? And you need that stability because of the fact that you are always going to transfer that energy from one to the other. So the problem comes from the fact that you cannot. It's harder to maintain the temperature of the heat block if it has a low capacity because it's going to lose energy very quickly around the nozzle. It's going to transfer that energy, and it's hard to compensate that exactly with the amount of energy you put in the heat block. So it's going to lose energy fast. It's going to get energy fast, and it's very hard to balance that properly. But if it has a high heat capacity, then the temperature will be more stable in a way that the energy may fluctuate as much, but the temperature won't fluctuate as much. Yeah. So the energy won't change. The fluctuation of the energy would be the same, whether it's low capacity or high heat capacity. However, what we are interested in is the temperature fluctuation, and the temperature fluctuation would be much less for the same energy fluctuation in a high heat capacity heat block than a low heat capacity heat block. Okay, everything makes sense now. Everything makes a lot of sense. Okay, so let's have a look. What's the heat capacity of aluminum compared to brass? Heat capacity aluminum. Okay, so the heat capacity of aluminum is specific heat capacity, molar heat capacity. Let's choose this one. So it's 0.99, and copper is 0.39. Okay, so aluminum is much higher than is double, is more than double the copper, and we just said that one is copper and one is aluminum. Okay, so that's interesting. So that means the high temperature one. By the way, I still don't understand why you need, because aluminum heat resistant is much more than 300, right? Why do you need? Yeah, I have another question for you guys, for the smart people out there. Why do you need to upgrade from aluminum to copper if you want to increase to 500 degree? I mean, aluminum cannot resist 500 degree. Aluminum, what can I say? Heat resistance? Does it has a heat resistance? Alloy aluminum melts at temperature approximately 655 degrees C. It boils at approximately, yeah, okay. Yeah, so okay, so 500 is too close to their melting temperature. Is that okay? So maybe at 500 is going to become soft. I mean, I don't know how how's the temperature affecting metal. Are they going softer and softer, or do they have a phase transition? I'm a polymer guy, not a metal guy. But my guess is maybe 500 is too close to that. So let's check copper heat resistance. So I guess copper is much higher. Temperature coefficient of copper, blah, blah. Is there some kind of heat resistance? Can we talk about heat resistance for copper? Blah, blah, blah. Copper, the temperature coefficient of copper near room temperature is blah. This means the temperature increase 1 degree, the resistance will increase. Yeah, but I'm interested in the heat, what, operational temperature? How do you call that in metal? Like melting temperature? Do they have a melting point? Oh, melting point. Okay, so the melting point of copper is 1000 degree, and the melting point on aluminum is I guess we just saw it, right? It's 600 degree, right? But let me double confirm. 600 degree. Okay. So it has to do with their melting point. Okay, now I understand. So the melting point of aluminum is 500, and then the melting point of this one is 1000. So they take some kind of margin, Okay, understandable. So that means, okay, so they sacrifice the heat capacity in order to have more heat resistance. I mean, yeah, I don't know if you call it heat resistance, but okay, I understand. The issue is that we are not in the ideal world, so we have thermal conductivity, thermal mass, thermal losses, and we come back to how fast you want to print. Also, with a lower heat capacity, it's easier for the heater to overshoot the value because it needs to dump more heat quicker. Yeah, good point, Zombie. The E3D Revo is a good example. It heats up quickly but struggles to keep stable temperature thanks to the small heat block. Okay, good to know. Now we start to understand, when we are going to study the different design, then oh yeah, that's a good point, because the volume of the heat block is also defining the heat capacity, right? Or how fast you want to melt the filament. Yeah, if the capacity was too low, every pulsation of the heater would make a big difference on heat. Yes, heat capacity is is how much thermal energy a unit volume of some materials can hold. Thermal mass is that heat capacity time how much material you have. Heat capacity is the material property. Thermal mass is geometry property. There is a better term for it, but I forgot at the moment. Yeah, okay, so let me check what is thermal mass. I was on the, so thermal mass. Okay, so the thermal mass. Thermal mass is a property of the mass of a building which enables to store heat, providing inertia against temperature fluctuation. It is sometimes known as thermal flywheel effect. For example, when outside temperatures are fluctuating throughout the day, large thermal mass within the insulated portion of a house can serve to flatten out the daily fluctuation. This is distinct from material insulative value, which reduces building thermal conductivity. Scientifically, thermal mass is equivalent to thermal capacitance or heat capacity. Oh, okay, okay. Oh, okay, okay. Yeah, incendium. Right on point. Right on point. So the heat capacity is material. So it's a material property, and then the thermal mass is the heat capacity multiplied by the volume. Kind of. I mean, I'm really oversimplifying, but if you have a high heat capacity material plus a large volume, then the thermal mass is very high. So okay, makes sense. So they're highly connected. So what we're interested in is a heat block with a very high thermal mass. So not only a material that has. So actually, the nickel plated copper, you can have a small aluminum heat block that have the same thermal mass as a big copper heat block. So that's how you can compensate. Yeah, okay, very good point. Is incendium. OneRise, if you print in high temperature, wouldn't you need a bigger gap between the hot end and the heat block? If you print in high temperature, wouldn't you need a bigger gap between the hot end and the heat block? Yeah, sorry, I don't understand. Maybe you can try to use the same vocabulary as I'm using, because the heat block is in the hot end. So I don't know how you can have gap between them. The joule per gram heat capacity will be misleading since the heat block have the same volume, not mass. A copper heat block is heavier, density needs to be. Oh, yeah. You're right, incendium. Aluminum loses something around 50% of their strength at 600 degrees. Okay. Well, it seems that they are melting at 600 degrees. So I think the melting temperature from Google of just regular aluminum is 630 or something. We just checked. The heat close to the cartridge is higher than the one reported by the sensor. The nozzle temperature, 600 degree, is a bit limit. Okay. Yeah, okay. Okay, got it. So we have understanding of all of this. Then next is that thing here. So this is the gray. The light gray is the heat sink. So it's basically responsible of, I guess, getting rid of the heat that goes through the heat break. So the heat break will, I guess, will break. So will stop as much as they can the heat, and then the heat sink will get rid of the rest of the energy that has somehow went through the heat break. I guess that's how it works. And then you have, so we won't talk about the cooling fan. So this is the cooling for the heat sink, that we won't talk about it. And then I think that's it, right? Is there anything else? So this thing here is just the the connection between the Bowden or whatever before and the hot end, right? So I don't think it's very important. So is that all? Nozzle, heat cartridge, thermocouple, heat block, heat break, and heat sink. That's what makes a nozzle. Or am I forgetting anything? Okay. So essentially, yeah, okay, great. So next is let's quickly go through this article. Now that we have our background on the hot end. So the hot end is one of the fundamental part of FDM, blah, blah, blah. This is, how the hot end works. The hot end element, blah, blah, extruded. So, yeah. Okay, so they have nozzle, heating block, temperature probe, heating cartridge, heat break, and heat sink. Okay, so we have all of these. Nozzle, it is the part of the hot end. Yeah, we know that. The system, there are multiple hot end system, although the most common are two, V6 system and MK8. Okay, so there's two systems. In addition to this, some recognized brands such as Ultimaker, BCN, 3D, and Race 3D have their own. So when they say system, I think they are referring to the connection between the nozzle and the heat block. So I think that's what they mean by system, the hot end system. So it seems that there is the V6 system and MK8. Okay, so maybe this is the V6, and so is that all about the threads? Like, what's the standard of the thread they are using? And then Ultimaker, BCN, and Race 3D are using different threads. Although both V6 and MKN nozzle have an, oh no, so the thread is the same, M6 times 1. Thread and may seems to be compatible at first glance. This is not the case. Dimensions differ considerably between the two. While the nozzle of the MK8 system have a length of 8 mm, those of the V6 system have a length of 5 mm. This implies that on printer where the level sensor is located on the head, the nozzle will be higher and will not be printable. Although modification can be made of the printer adapt, but if it's okay, so the MK8 is 8 mm length and the V6 is 5 mm end. So which means, yeah, so if you put a V6 on an MK8, then you will have an issue because you will have a gap where the material can go, and that's bad for the flow. And if you put an MK8 in a V6, then what's the problem? This implies that on printers where the level sensor is located on the head, the nozzle will be higher and will not be printable. Yeah, I mean, you can, I understand you cannot put the V6 on an MK8, but you can put an MK8 on a V6, right? That shouldn't be an issue. I mean, you have to re-level the bed. That's not a problem. And maybe maybe you need more temperature to heat up that extra millimeter, 3 mm, but that's it, right? You could. Sounds like a hot end assembly. Good background, an hour in. Yeah. Do you remember I said we will take 10 to 15 minutes to get the basic of a hot end? And it's been 1 hour and 12 minutes that we are still into understanding a hot end. But again, you guys know much more than me, so I need to get up to speed first. How far the PTFE tube extend is important for design too. Yeah, I guess PTFE is part of the heat break, right? So it would be called the heat break. Or is there another heat break somewhere? Because PTFE, that's the goal, no? A small background. Yeah. A very quick very quick, going back to basic background. V6 is the flatter nozzle. Oh, you mean okay. So you mean, okay, so sorry. So the V6 was that one. So this thread should be 5 mm, and this is the MK8. So this thread should be 8 mm tall, apparently. And apparently these two are the main standard. So they all use M6 thread, and one is 5 mm, one is 8 mm. The other way around, V6, it's the longer threaded. Really? Because they just said the MK8 system have a length of 8 mm. Those of the V6 system have a length of 5 mm. So when they say the length, I assume they are talking about the length of the threaded part, right? Not the whole nozzle. Oh wait, so what are they talking about when they say the length? Which part? MK8 is Creality and is garbage. Okay, V6 is what everyone else uses. No PTFE in the filament path. Heat break is the tube threaded. Blah, blah. Thread, it's the same size, but the length is different. Yeah, you can put a V6 on an MK8. Yes. PTFE stops somewhere in the heat sink. The heat break should be separate. But what's the point of the PTFE? I thought it was also to insulate the heat. But wait, so who said? Yeah, so FDEF patch, you said the V6 is the longer threaded. Okay, so maybe what do they mean by the length is 8 mm? I thought they are talking about the length of the thread here, like from here to there. On a V6, it's from here to there is 5 mm. On an MK8, from here to there, it's 8 mm. That's what I understand. So that's why you cannot thread them. I mean, you can thread them in each other's heat block, right? But if you put a MK8 in a V6, then you won't be able to thread it all the way through because there's only 5 mm. So you will have 3 mm of threads that cannot go inside. And the other way around, if you put the V6 in an MK8, then you will thread all the way through, but there will be a 3 mm gap inside. So that's what I understand. The purpose of the PTFE is to guide the hide into the slide of plied in the sky of the... I don't understand anything. PTFE in the heat break is what Creality does, and it's garbage. Probably how much it sticks out. I think that measurement is bad. The threads of MK8 is 5 mm. Okay, so the information we have is not good. But that's not good. Article is bad. Okay, so they are both 5 mm. So they are both the same. It's the very end of the filament path in the PTFE extends too far in the heat sink. The PTFE gets too hot and limits the safe max temperature of the hot end. I don't like when we don't have good information. But okay, let's not verify. Let's just so FDEF patch confirmed that whether it's the V6 or the MK8, it's both 5 mm. So at the end of the day, you don't have multiple systems. If the V6 system is the same as the MK8 because they have the same threads and they have the same length, then they are basically the same. So there's only one system. So maybe they need to update their article. Okay, diameter. Well, we don't need to go into that. We know that there is different diameter nozzle, blah, blah, blah. Volcano, supervolcano are increasing the length of the hot end. For the nozzle above, blah, 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 so we don't care. 3D Solex have some innovative design, core heating, okay, so that's some geometry. Okay, and then you have the material. The brass is the most common material. The main advantage is the low cost, ease of manufacture, and high coefficient of thermal transmission. Among its main drawback is low wear resistance, low resistance to high temperature since it's not available. Oh, I didn't know. I didn't know you could not use a brass nozzle to print above 300 degree. What is the brass melting temperature? Why do they use Fahrenheit? Brass, yeah, I mean 930 degrees, so that should be fine. All metal hot end means the PTFE stops for enough away to be safe at higher temperature. No, the MK8, it's a 5 millimeter thread. The V6 is 6 millimeter plus 1 millimeter non-threaded. Okay, got it. So it is two different systems. V6 can fit in a MK8 block because it has longer thread, but an MK8 will not fully sit in a V6 block. Okay, got it. Okay, so it's the other way around. Okay, I understand. You need a coated copper nozzle for high temperature. But why? I mean, 400 degree doesn't seem to be very high if the melting temperature of brass is around 1000 degree. But anyway, so they say that the biggest upside is the thermal transmission. The thermal transmission. Okay. So it means from the heat block to the material. So the nozzle is in between. So we need the nozzle to transmit that energy very well. So we don't really care about. Oh, okay. So maybe that's another question. The nozzle heat capacity, is that better to be low or high? Because the conductivity of the nozzle has to be high. Let me think. Because if the material needs to receive energy, the heat block. So you have the heat block that has that big mass of energy that you can draw from, and then the material need to draw energy from that heat block, and then you have the nozzle in between. So it's better that the nozzle doesn't absorb all that energy. So maybe it's better to have a low heat capacity nozzle and a high conductivity. I guess something like this. Yeah, I'm not sure actually. I need to think about it. Nickel-plated brass. It is becoming the standard in the highest quality nozzle. It is a brass nozzle to which a fine nickel coating has been applied. This surface treatment gives you greater wear resistance, lower coefficient of friction, and high corrosion resistance. This makes them have a durability that is superior to brass nozzle. Okay. Nickel-plated copper, the specific material for printing with high temperature filament. It must be combined with a heating block of the same material, allows temperature up to 500 degrees. But again, I don't understand why, because copper and brass has the same melting temperature. Melting temperature. So I don't understand why one would be better than the other one. You see, brass is 930 degrees C and copper is 1084 degrees C. So, I mean, it's more or less the same, right? So I don't understand why you need to upgrade your nozzle in order to print at a higher temperature. It doesn't make sense to me. For the heat block, I understand going from aluminum to a copper, because the aluminum is 600 degrees. So if you print at 500 degrees, then that's a bad idea. But the nozzle, it looks like brass is fine. I know tool steel is worse because it has low conductivity, high resistance to heat change. Yeah, conductivity, I agree. I think it's better for the nozzle to have a high conductivity because the goal is for the heat block to pass the energy to the material. And the heat block needs to have a high heat capacity so that it have a lot of energy that the material can draw from. And it's easier for the heat cartridge to to put back that energy inside so that the temperature is stable. This I understand. For the nozzle, I understand that it has to has a good heat conductivity because he's in between. So basically, he's in the way. We wish we didn't have that guy, that nozzle, and then it would transfer directly to the material, but that's not possible, right? But for the heat capacity, I don't have any logical explanation that would say it's better that it has a high heat capacity or a low heat capacity. That's all the information. Tungsten carbide nozzle is the best there is right now. Well, it depends what do you mean by best? Because I'm pretty sure the price is not the best compared to brass. I think the nozzle is only for conductivity and non-filament sticking. It's only necessary for abrasive filament. Otherwise, brass nozzle are good enough. Yeah, okay. Then we agree on that. It is copper alloy that is used. Okay. I think brass becomes smooth before copper. Okay. Brass and copper get gummy before they melt. Not sure if the difference between them. Are. Oh, okay. Yeah, it could be depend on what's what's their behavior at a different temperatures. Hardened steel or tool steel, they stand out for their high abrasion resistance. They have been designed to work with highly abrasive filament, blah, blah, blah. It is essential materials such as metal filament or woods reinforced, blah, blah, blah. The main disadvantage is lower surface print quality than the previous one. Wait, the main disadvantage is that they usually provide lower surface print quality, but why? Although they are generally available in size 0.4, it is recommended to use greater 0.05 to avoid obstruction. Although they can withstand 500 degrees C, it's not recommended to use them with abrasive material above 350. But why? I thought the main issue of hardened steel was the conductivity, the fact that they have a lower heat conductivity, thermal conductivity compared to brass. I don't understand why they usually provide lower surface quality. I don't understand. And I also don't understand why you cannot use them above 350 if you use abrasive material. Is that the higher the temperature, the less abrasive resistant it is? That could make sense. Maybe they get softer as the temperature raises, so that they get less abrasive resistance. Okay, that could make sense. That's logical. Is the finish less smooth at the nozzle? Oh, that's a good point. Maybe it's harder to CNC a hardened steel compared to brass. So maybe the finishes on the hardened steel nozzle are less defined than a brass nozzle. That's a good point. Tungsten may be expensive up front, but it is last forever. Then the price is cheaper. Yeah, could be. That's why it's important to define what's best. What's best for what? Hardened steel is for abrasive material, yeah. Or are they referring to the fluctuation in flow? Yeah, it could be also. It could be the fact that the thermal conductivity is bad and that the flow is very different during the printing. Then you will have different extrusion temperature, so that you will have a bad surface quality. That also makes sense. And then you have stainless steel. What's the difference between hardened steel and stainless steel? So hardened steel, I think, is steel that you have heat treated, right? Hardened steel is often used for a medium or high carbon steel that has been given heat treatment and then quench, followed by tempering. Okay, that makes sense. And then stainless steel. Stainless steel is an alloy of iron that is resistant to rusting. It contains at least 11% chromium. And okay, so it's a different alloy. Okay, got it. Although it may look similar to the previous one, and many users acquire it for abrasive filament, this is not their main application, as their abrasion resistance is much lower than the previous one. Oh, I didn't know that. This type of nozzle are mainly used in medical or food application, since due to their high corrosion resistance, they do not give off toxic particles that can be mixed with the molten materials. It is probably the least common materials in the manufacture of nozzle, like nickel-plated copper nozzle. They are suitable for high temperature applications supporting up to 500 degrees. Oh, okay. Well, that would be a good topic in the food safety print buster topic. What's the melting temperature of stainless steel? Whoa, okay. 1,400 degree. Okay, interesting. But I don't think there's anyone that used that nozzle for to make medical stuff or food application, or maybe there is, I don't know. Brass or copper with ruby tip. Yeah, okay, I know that one. By the way, all the ceramic nozzle, I mean the ceramic hybrid nozzle, the biggest issue when you have to look at this, because there is this new diamond nozzle as well. I think the most important is the weakest part of the nozzle, because this ruby nozzle, remember, there was a big review that was talking about, okay, the ruby nozzle is great, it's hard, but all the inside were completely worn out, and then it completely destroyed the good flow of the filament. So I've seen the YouTube video that was explaining all of this. Like I think he even cut the nozzle in half. So that's always the problem of having a ceramic hybrid nozzle, is you will always, the most important is how strong or how resistant is the weakest part of the nozzle. So you can have, because can you imagine a brass nozzle with a diamond tip? Now it doesn't really help, right? Even if you have the tip that is diamond, okay, the tip is going to stay 0.4, but the whole nozzle inside, then it completely messes up the flow. So yeah, just one point I want you to highlight, but we don't have to read all of this stuff. The heating block, we already read about it. Temperature probe. Okay, so there's different way of I didn't know there's different way of knowing the temperature. There are multiple different types, which is different factors and parameter. It may be necessary to modify the printer firmware or even add additional electricity. So thermistor, it's the most common. It has high accuracy at low temperature, and its price is very economical. Disadvantage is not suitable for temperature above 285. Okay, so there is the first thing that is called a thermistor, and then the second is called a thermocouple. They allow to measure very high temperature accurately. However, when calibrated for a specific range, they cannot measure high or low temperature with high precision at the same time. Although they are usually inexpensive, they require additional electronics to convert the signal. One of their main drawbacks is that they are sensitive to electromagnetic noise, so their cable must be shielded and kept away for power supply call. Okay, so what's the technology difference between a thermistor and a thermocouple? A thermistor is a resistant thermometer or a resistor whose resistance is dependent on the temperature. Okay, makes sense. And what's a thermocouple? And a thermocouple is an electrical device consisting of two distinct. Okay, so it's based on that effect. So what was the other one? The thermistor is based on the material you're using. So you will put a material inside the heat block, and then we know the thermal resistance of that material, and then depending on its resistance, then you will define the temperature. And then the thermocouple is based on a different effect, which is called the thermoelectric effect. Is the direct conversion of temperature difference of electric voltage or vice versa, blah, blah, blah. creating a temperature difference, the atomic scale, blah blah blah. Yeah, okay. Maybe we don't need to go into details, but it seems to be a different thing, different effect. And then you have the PT100 probe. They have almost completely replaced the use of thermocouples. They allow to measure temperatures up to 500 degrees with precision, combining the advantage of thermistors and thermocouple. In return, its price is the highest and requires additional electronics. Okay, so apparently now they don't use thermistor or thermocouple anymore because we have a new MVP, which is this guy. But how does it work? What's the difference between a thermocouple and a PT100? Blah blah. Temperature range. Yeah, but I'm interested in what's the technology? What's the RTD technology? I have never heard about that sensor, by the way. I have heard about thermistor. I have heard about thermocouple. I have never known what's the difference between both, but I have never heard about the PT100 sensor. I don't even know how it works. The most common type of platinum resistant thermometer. Often resistance thermometers are generally called PT100 sensor, even though in reality they may not be the PT100 type. PT refers to that the sensor is made from platinum. 100 refer to that at 0 sensor it has resistance of 100. Oh, but that's the same as the thermistor. It's based on the what is this? It's based on the material resistance, thermal resistance. Several ways on the temperature sensor designed to get the best measurement of your process. Yeah, so that's the same. So they use platinum, but the thermistor is the same. They also use it's the same technology. Why do they call it differently? Do you guys know why is it different? It's also a thermistor. The thermistor is exactly the definition of a thermistor. Thermistor is a resistant thermometer. Resistor whose resistance is dependent on temperature. The term of combination of thermal and resistor is made a metallic oxide pressed into a BD cylinder shape and then encapsulated with an impermeable material such as epoxy or glass. Yeah, and I guess you can choose different type of material, I guess. And then some of the material can be used, and platinum can be used, I guess. Yeah, I don't know. That's sounds like this technology is based on one effect. This technology is based on another effect, and the PT100 probe for me is based on the first effect. They just use apparently a good material, which is platinum. Hardened steel and stainless steel are totally different alloy. Yeah, I just learned that. I see what the article is saying. You can buy very cheap hardened nozzle or high quality one. I don't really see the goal of those ruby nozzle. Yeah. It looks cool. Most where the nozzle is at the tip. Yeah, I mean, yes. But if you pay €100, which is I think the price of a ruby nozzle, then you want it to last, at least as long as you would if you buy €100 worth of brass nozzle. But from the YouTube video I've seen, the review, it seems that it does not, because the brass inside is going to wear out, and then you're going to have a big ball inside, empty ball, and then that tip, and then it's very difficult to feed the material. Diamond have short hardness of 10, tungsten of 9. 3D printer almost never use thermocouples. Okay. I've seen a lot of people calling it thermocouples, but I don't know if it is thermocouples. Unpopular opinion, but I would say stay with brass nozzle unless you need abrasion resistance. I mean, good quality brass nozzle are not expensive and they have good thermal conductivity. Yeah, I agree. I ordered a P100, but don't know how it works. Well, now you know. It's basically a thermistor, but with platinum. You need a proper interface for it, as well as PT1000. PT100 or PT1000 is for higher than 300 degree. Most main boards do not support PT100 natively. Some newer high-end boards do. Okay. I don't know why they wouldn't, because it's just a resistivity, right? It's just a resistance. So they just give one information. So I don't understand why some board wouldn't why you need a high-end board to read that information, because it's basically only an electric pulse, or like some kind of information that I don't understand. But I'm very bad at electronics, so we'll have to look into that also. I believe they are more accurate. Sounds like a thermistor. Yeah, exactly. Art Match Animation. It's a thermistor plus. PT100 needs an extra board. Oh, okay, so you need somehow to translate some of the information it has, right? So you have to process the information. Okay. I only have a copper nozzle because it came with a copper block. It came with the copper block. Okay. Okay, PT100 are low resistance RTD, so it needs a special circuit to be read it properly, like an amplifier thermistor. And RTDs are high resistance sensor and can be directly used by a microcontroller. Okay. Oh, FDAF Patch is a smart guy. He answered most of our question, like Zombie, FDAF Patch, all you guys in the chat. You guys are so smart. You impress me. Either you impress me, either I impress myself with the non-knowledge I have. Also, PT100 and PT1000 is a PTC thermistor. The common Semitech 104 GT-2 and NTC 3950 is NTC. PTC is positive temperature. Oh, okay. I was about to I was about to say I don't know what is ATC. Okay, so what's the difference between PTC and NTC? So thermistor, NPC, or PTC. They are available in can provide inrush current protection in various equipment, blah, blah. Thermistor, there's no. They are available with either negative temperature or NTC of resistance of positive temperature resistance, coefficient of resistance. The difference being that NTC thermistor reduce the resistance as the temperature increase, while okay. So when the temperature for NTC, when the temperature increase, then the resistance will decrease. But for PTC, when the temperature increase, then the resistance will also increase. Oh, okay. So that's the okay. So in thermistors, you have so you have two sub-branch of thermistor, NPC and PTC. Got it. I know a little bit about electronics as an electrical engineer. Yeah, a little bit, Zombie. If you understand electronics, one needs an amplifier, an operational amplifier, and the other needs a resistor voltage divider to be measured. Yeah, that makes sense. I mean, FDAF Patch, you explained it very well. I completely understand. NTC only uses current when it gets hot. Okay. I'm a mechatronics engineer. I think I'm supposed to know these things. Mechatronics is these kind of robots that move, right? Mechatronics. Yeah, it's this kind of thing like robots and stuff, or is that just is that how do you call it? Is that the misconception of mechatronics? Because for me, mechatronics is all of these robots that are moving and stuff. Mechatronics is multidisciplinary field that refers to the skill set needed in the contemporary advanced automated manufacturing industry. Mechanics, electronics, computing, mechatronics specialists create simpler, smarter systems. Okay, so basically, you know everything. That's what mechatronic means. Yeah, okay, yeah, that's what I just said. Material processing, automotive, aerospace, medical, electronic system, mechanical system, computers, controls. Yeah, okay. So basically, being a mechatronics engineer is the top of the top. So thank you for being in the chat. I think it would be very useful to keep you around when we are learning this kind of thing. We need more mechatronics engineer in our community. So now here's the question, because I know Zombie is an electronic or electric engineer. I don't know if there is any difference. So is the mechatronics electronic knowledge better than an only electronic engineer? Now here's the question. My guess is no, because I think mechatronics you would have to compromise, right? Rather than the electronic engineer would know pretty much everything about his domain, I guess. But anyway, it's great to have all of these different backgrounds in chat. Heating cartridge. Okay, so we talked about the power. There's no problem. Heat break. One of the most important element of the hot end. Yeah. Its function is to separate the hot zone and the cold zone. Yeah. Okay. Blah blah. It is the component that will define whether a hot end is all metal type or not. Okay, so do you remember when we talk about all metal hot end or not all metal hot end? So it will all depend on your heat break design. So depending on whether the interior is Teflon coated or not. It is manufactured with low coefficient thermal expansion material, such as stainless steel, to increase the thermal breakage effect. The highest quality ones are produced in titanium or with bimetallic combination like slice engineering. Okay, so let's stop a little bit there. So the heat break, okay, the thing that is here. The heat break, okay, so you will have a PTFE tube here. In the non-all metal hot end, you will have a PTFE tube here. That will make sure, so you will have that design, similar design, where you will have a very thin transmission between the hot end and the cold end, and on top you will have a PTFE tube here to avoid that whatever heat has been transmitted will be transmitted to the filament. PTFE tube is low friction and it's plastic, right? It's a polymer, so it's the conductivity is extremely low. Okay, so but you have some other. It is manufactured with low coefficient of thermal expansion of the acidity to increase the thermal breakage. Okay, so it seems like low coefficient of thermal. Oh, sorry, thermal transmission. Sorry. Somehow I read thermal expansion or something like this. But okay, low coefficient of thermal transmission of the acidity to increase the thermal breakage. Okay, so that means it will have difficulty to transfer the heat from here to there. Okay, makes sense. And you have bimetallic combination. Okay, so I guess titanium has an even. So what's the heat transmission coefficient of titanium? So the thermal conductivity of titanium is 17. So watt per millikelvin. and the thermal conductivity of stainless steel is 15. Oh, wait. Oh, so stainless steel is better than titanium. I mean, maybe they use different alloy, but from, you see, stainless steel is 15 watt per millikelvin, and titanium is 17 watt per millikelvin, which means there is more that will be transferred with titanium. So why does the article says that the highest quality ones are produced in titanium? Highest quality in terms of what? Bimetallic, I can understand. I mean, the best heat break is to have as many heat transfer between different material as possible, as many interface as possible. You see, you have some interface here, right? Different interfaces. So bimetallic will have, also different interface, and I guess they can also play with the heat, the thermal conductivity of the different metal. So, but I still don't understand why titanium would be. It seems that in terms of a material, stainless steel is better. Jack of all trade, master of none. Hi, Francis Bellon. Zirconia as a heat break material is also starting to get popular. Okay. Zirconia. Whoa. 5. Oh, it has a very, very, very low thermal conductivity. Okay, so I guess if it's processed well, if you can see that, and if it's not too expensive, then it's great. Zirconia. I didn't know a material was called zirconia. Interesting. I'm sure Zombie knows more specialized topic and a lot more of AC than me. Yeah, I didn't want to create any competition. Huh? I was just joking. But I really like the fact that we have many specialized engineer in the chat. That really helps. I think the titanium one is because it sounds cool. Yeah, it could be a marketing way, right? We have a titanium heat break. It's like, I mean, it's titanium. Yeah, but does it work well? Are you kidding me? It's titanium. Yeah, but it's quite expensive. What? But it's titanium. We send that to space. Come on. Oh, okay. Let me buy one. The bimetallic use stainless. Okay, stainless steel. So bimetallic means what? Means two different metal, right? So stainless steel and what? Or it's just the fact that they use an interface. So it's both stainless steel, but they have like some kind of air interface in between. I have titanium copper heat break. It works well. Okay. What did you say? Titanium copper? Is that a thing? So it's like a mix. Titanium copper. Okay, so it's alloy copper. Titanium copper is a copper alloy having titanium as the main additive element. Okay. Yeah, I mean, I guess in metal you can have so many different type, right? Hi, CDHP. Bad article. Yeah, I mean, we've pointed out a couple of issue with that article. Titanium might be able to made thinner without breaking. That's a good point. Insanium, maybe the processability of titanium allows more accurate design. Stainless steel is better than titanium, yeah, at least from the data. And very abrasive resistance. Which one is abrasive resistant? Titanium or stainless steel? In the Rockwell scale, which one is the hardest? It's a ceramic type material. Oh, zirconia is a ceramic type. Okay. Oh, but then but how do you process that? That's unprocessable. So you would have to have a, you will still have to have a stainless steel shell or a design, and then you put zirconia inside as a insulator or something like this. Titanium is what makes 3D printers crave marketing. Bimetal heat break. From Google, the thermal conductivity of commercially pure titanium grade 2 is 16 watt per millikelvin. Oh, millikelvin or metakelvin? The thermal conductivity of titanium, blah, blah, grade 5 is 6.7. Oh, okay. So there is a big difference depending on the grade you're using. Yeah, it makes sense. I mean, there's so many different alloy. So maybe they are using a titanium alloy that has a lower thermal conductivity as stainless steel. For example, the one you mentioned, incendium, like the grade 5. Pure titanium is rarely used for much. Yeah, okay. Got it. Thank you for the info, incendium. And then heat sink. Now the function to cool the cold down, blah, 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 blah. Yeah, so I guess for the heat sink is pretty much the same for all of them, right? It's all about how you design that surface interface between the air and your metal part, and I guess also the flow of your fan. How to choose the right hot end, blah, blah, blah. Okay, and this is what we're going to. Okay, so we finished the background of the hot end. After 2 hours of stream. So what shall we do? Shall we stop here and then we continue on Saturday for the hangout? So basically, we keep the Printbusters for really going deep into the hot end design and the different materials and the different ways. And then for the Polymaker hangout on Saturday, then we go through the different technologies and stuff, like how they design their stuff. So looks like we know everything now. This is the socks, the heat block. This is the nozzle. This is the thermistor or a thermocouple, depending on what they use. So this is number 10. No, sorry. This is the big one. This is the heater cartridge. Sorry. And this is number 9, the thermistor. Okay, so they use a thermistor. They don't use a thermocouple, and then we know the difference. And then we would just need to know what thermistor they use, what type of material. Is that a P100 or not? Most likely not, because it seems that if you use platinum, then you use a different name somehow. And then the nozzle, you have a V6, and then we know we have the MK8 stuff system and the V6 system. Yeah, we learned a lot today. And that's, I guess, the heat break, and that's the heat sink, and that's for the cooling that we said we won't talk about it today, and that's the connection with. Yeah, I guess we learned a lot today. We did learn a lot. So what do you think? Okay, part 2. So we do a part 2. Okay, so let's do the giveaway now, and then leave the rest for maybe for Saturday. So Saturday is going to be on Twitch. This is already good info. Don't rush it. Yeah. And maybe we need to let it sink a little bit. All the thing that we learned about the nozzle stuff, maybe we need to let it sink. And then on Saturday, then we go back to the different nozzle design. And then it will be much easier for us to understand the differences between all the different nozzles. By the way, knowing a little of everything, being specialist of everything, that's the way of mechatronics. Yeah, I've seen that. You basically know all the fields. I will compile a list of all the major hotends. That would be awesome, Zombie, if you can do that. I don't know if you were there at the beginning of the stream, but I've chosen E3D, Slice Engineering, Dice Design, and Microswiss. And maybe we can talk a little bit about the product print. But that's the 4 main company that I want to study their nozzle. Some more awesomeness before the giveaway. That classic design nowadays with Revo Rapido, there is no more heat block. No more heat block? Oh, so you mean the cartridge, the thermal cartridge is straight into the nozzle? Interesting. I just created a hot end. Please add your favorite hot end, as much info as about it. Oh, great. So did you create that as a Printbuster topic? Yeah, perfect. So guys, Zombie just created hot ends for Printbuster topic. So if you want to discuss about hot end, whether titanium is better than stainless steel or not, whether Ruby nozzle is a marketing thing or is a real use, all of these debate and topics and science around hot ends, feel free to join our Discord, discord.polymaker.com, and then let's talk about it. Let's share more about it. Thank you, Zombie. I think titanium heat breaks got popular because E3D started using it. Yeah, FDAF patch. That's exactly what I want to do in Printbusters. I want to differentiate the common knowledge that sometimes this knowledge come from marketing or come from some stuff to the scientific knowledge. I want to make a difference. Did you want to jump into the Discord voice chat at all? If you have time, we should do that sometime. Yeah, Zombie. Like I said, I think I still have 1 or 2 weeks. Well, actually 2 weeks before our big half-year meeting. And after that, then I will be much freer, and then we can get back to some nice discussion. But the last month and next weeks, I still need to prepare all of this. Today is part 0. Yeah, yeah, you're right, Kenneth. We can do part 1 next time. Yeah. Fatius, okay, I mean, yeah, I didn't know about, I discovered that company last stream, the dragon stuff, and yeah, that's another interesting one. Yeah, of course. Let's add it in the list. E3D, slice engineering, dice design, microswiss, and Fatius. Yeah, let's put it inside. Fatius. Yeah, okay, I got it. It will be on the list. I do have 3 sports, blah blah. Those one just say are so unpopular. Oh, you mean they are so unpopular? Well, for me, E3D, slice engineering, dice design, microswiss, I don't know. I've seen them around. I don't think they are that unpopular. I think they are pretty popular. Maybe that one. Maybe Protoprint would be unpopular because I haven't heard about it. But the other, I think, are pretty popular. Keeping quiet. I'm still tired from Amazon Prime Day live stream. Oh yeah, there is some interesting live stream on Amazon. Okay. Waiting for the Revo Obsidian nozzle. Hi, Josiah. VZLSD hot end is pretty cool. I don't know what this one is, but okay. So let's check that in part 2 or part 1 on Saturday. Let's go through all of these nozzles. Fetches Bottle design, dice design? No way. I didn't know that. Acquire dice design. Are you sure? Maybe not. Maybe not. If you have an article, can you share it on our Discord, hot end Discord? And that's interesting. That would be interesting. Okay, guys. I think I caught up with all the chat. So let's bring some more awesomeness. Well, actually, 27 viewers, 35 entries. So I think everyone is there. Are you guys ready? We're gonna do today's giveaway for hot end Printbusters in 5, 3, 4, 2, 1. And the winner is going to be, let me check. Is there any mark here? Oh, Builder's Mark. Just enter. Perfect. So it's going to be Builder's Mark. Builder's Mark is going to win today's giveaway. You ready? Oh, Kevin Tucker. I need more of that amazing Galaxy Dark Blue PLA. Yeah, Zombie, DM me on Discord. I will send you a spool. Congratulations, Kevin Tucker. You have 10 seconds. You have 10 seconds to show that you're here in 10, 9, 8, 7, 6, 5, 4, 3. Yeah, Kevin Tucker, congratulations. Congratulations for winning. I saw my name 4 times. Yeah, I mean, it was almost art animation, right? And then at the end, it just switched to Kevin. So congratulations, Kevin. You can, yeah, Robert, I've seen your email. I will get to that. You can send me an email here, Kevin Tucker, but I think I've seen your name before. So I guess we are, you know already how to contact. So thank you very much for joining this this special episode of PRINTBUSTERS. If you like this kind of episode, let me know. Let me know if you like, you know, the kind of episode where we dive into a specific part of the 3D printer. Because there is the extruder also that is interesting, the different type of extruders, the different type of firmwares, the different type of slicers, the different type of motion system, the different types of bed surfaces. I mean, you know, we can spend a year just learning about printers, learning properly about printers. What are the difference? What are the science behind the different technologies that 3D printer company are pushing forward. So if you like this time of PRINTBUSTERS episode where we choose one thing, then let me know, and we can do more of this. Because I didn't know if it was too basic for you guys, because I know, you know, you guys are top level in terms of 3D printing knowledge. So I don't know if it's too basics for you. If it's so, then we can dive into deeper topics, which will be more in polymers, because that's where I can bring more knowledge. But if you like, even if it's basics, then let me know. We can continue. Just me. I tried emailing you, but you haven't emailed me the link yet. Okay, let me get to that. Just me. Let me get to that. This is why you should build a Voron, because then you deep dive into everything. Yeah, I wish I had time to build a Voron. We could do that on stream, because then we would have time. We would discover. Maybe a couple of words on that rip wrap diamond hotend next time. Yeah, we could. Feel free to put that on the Discord, and then we'll go through the Discord discussion during our next stream, and then we'll talk about these. This has been a lot of fun, the mechanics and chemistry both. Okay, great. I might have an easier build for you to do if you want to build a printer. I mean, at some point I will have to build a printer, right? If I really want to get into that, then I will have to build one, right? So that I have exactly all the pieces to do that. Okay, thank you again, everyone, for joining today's stream. And then I will see you again either Saturday at 12 p.m. EST on Twitch for our Polymaker Hangout, where we talk about different stuff. And most likely we're going to talk about hotend in this Hangout. And then next Tuesday, 9 p.m. for the Q&A. It's also available on Facebook and on Twitter. And otherwise, next week, Thursday, for another episode of PRINTBUSTERS. Thank you, everyone, again. Have a good one, everyone.